Welcome to another edition of Tales of the Workshop. Today we're going to feature an RLC circuit that is powered from a three-phase transformer. Obviously, we've got an awful lot going on here behind me in this circuit. We've got a delta connected primary with a Y connected secondary with an input voltage of 4160, that's a phase value, and a secondary voltage of 347 volts. That's going to power an RLC three-phase circuit, and if you haven't been able to distinguish this, this is a parallel circuit. I've got a resistive load that is connected in delta with a resistance of 29 ohms per phase. I have a Y-connected capacitor bank with a capacitor reactance of 13 ohms per phase, and finally I have an inductive load that is Y-connected with an inductive reactance of 18.7 ohms per phase. So grab a pen, pencil, a notepad, and don't forget that scientific calculator, and we're going to dive right in and go through the process of how to calculate for all of these missing values. We'll be right back. The first step in approaching this problem is to start establishing values here at the secondary of my transformer. I have a given value of 347 volts. That is per phase, and that's what this P stands for. I have the voltage and the phase. The L will stand for the voltage on the line. I'm going to have to take this phase voltage and I'm going to have to multiply it by the square root of 3, or in our case, 1.732. So if you follow me down to the other end of the whiteboard, and we're going to start with step 1, and we're going to continue on from there. First step is going to be to compute or calculate the value of line voltage based off of the phase value. Now the phase value was 347 volts. 347 volts. Now, in order to do this for a transformer, your E line is going to be equal to taking your phase value and you're going to multiply it by the square root of 3. Or in our case, I can put down, why don't we just take the eraser? 1.732. Entering that, E line, so 347 volts multiplied by your 1.732. And you should be getting, if you've done this accurately, a value of 601 volts. Now that's been rounded to 2 decimal places. So I'm going to go and input this on the board, and we're going to just keep moving along. Now that I calculated the line value of the voltage on the secondary, it's a matter of transposing this 601 volts AC to the line values for each of my 3 loads. Because if we see, if I've got 601 volts from line to line, well, I'm going to have 601 volts from this phase of X3 to X1, X2 to X3, and then X1 to X2. So it's a simple matter of taking this 601 volts and transposing it across all these empty values we see listed on the board. So 601, 601, 601. Now, I've also got a little shortcut. Right here, this is a delta connected load. And one of the things about the delta connection is that E line is equal to E phase. So that 601 volts across the line will actually be the same
value across the phases. So I can actually just take the 601 and add it here. So my table is starting to fill up. Now, we've got two Y-connected loads, capacitive and inductive. Now, we don't have to take into consideration anything about phase angle, not at this point in time. What we're going to do is try and get the phase value of the voltage for the capacitive bank as well as for the inductive bank. Now, the fact is they are both Y-connected. So this calculation will apply to both of those loads. So what we're going to do is we'll take the line value and we're going to divide that by the square root of 3, which is 1.732, which we're going to do on the whiteboard. So I think you're right.
When we calculated the line value for the secondary of the transformer, it was a simple matter of carrying over those values to each of the loads within our circuit. Now, we're at the point where we're working across the capacitive load bank, where I've got to go backwards now and find for the phase values of each of the capacitors. And that means then that I'm going to use the line value of voltage, and we're going to calculate phase values. Now the formula is going to look an awful lot like this. So E phase is going to equal to E line, but we're going to divide it by the root of 3. I could simplify this and write down E line divided by 1.732. Inputting this into a calculator, you should be getting, for a phase value, 347 volts AC. Now the nice thing about this is that both my capacitive bank as well as my inductive bank are Y connected, pardon me. And this 347 volts would apply as a phase value to both of those load banks. So this one calculation, it's going to pay off dividends because I've only had to do it once, but it applies in several instances. So we're going to go ahead and put that in, and then we're going to come back and start calculating current.
Now that I've calculated the phase values across my capacitive load bank and my inductive load bank, what I'm going to do now is I'm going to use the phase value of voltage combined with the value of capacitive reactance, and I'm going to figure out what is the current draw of each of the capacitors in all three that comprise my bank. So we're going to work with phase values in order to calculate the current. Once I have that, then we're going to go and do the calculation to get line values of current.
So continuing on, we're going to calculate the amount of current each of the capacitors is going to draw per phase. Now we're going to be using the value of voltage across the phase, and we're going to divide that by the value of capacitive reactance. So it's a simple Ohm's law. So first thing we're going to do is we're going to write out the formula. Current, or I, phase is equal to the voltage across the phase divided by your capacitive reactance, which is X sub C. And then we're going to input those values. We calculated 347 volts divided by, what was the capacitive reactance? It was 13 ohms. In this case, that's going to give us 26.69 amperes. Again, a very straightforward formula. We're using Ohm's law, but we're just making sure that we're putting the proper notation so that we can't get lost or off track. When we're dealing with circuits that are as complex as this, I know, speaking from experience, I take the time to write everything out so that I can make sure that my work is accurate. So enough said, let's go and input that into our table, and we're just going to keep cracking on.
Now that we've calculated the value of current that each of these capacitors is going to draw for our capacitive load bank, now it requires us to figure out what is the line value of current. But remember, this is a Y connection, and one of the characteristics of a Y connection is that, let's write this down, that I phase is equal to I line. If we look at it, if I was to eliminate one of these, this looks an awful lot like a series circuit. And what does the current do at any point in the series circuit? It remains the same. So in effect, we're using the characteristics of a series circuit. So this 26.69 amperes, well, that value isn't going to change in a Y connection. So we can actually take the 26.69 and put it down here as a line value. And that's exactly what I'm going to do next. Now, the only thing that remains is I want to calculate for the value of reactive power that my capacitive load bank is going to generate. Remember that capacitors generate reactive power. What we're going to do, again, Ohm's law, we're going to take the line values of voltage and current, multiply them, as well as multiply it, because it's three-phase, by the 1.732, or the square root of 3, and that's going to give us the total amount of power that this bank of capacitors is going to generate. So follow me down there, and let's do those calculations right now.
Once we've calculated values for line current, now we're looking for the overall power that the capacitors are going to generate. Now, power is represented by volt, amps, reactive, and sub C, because they are capacitors. And this is a trig formula where we're going to take the value of line voltage, we're going to multiply it by the value of line current. And then again, this is a three-phase capacitor bank. We are going to have to, we are required to multiply it either by the root of 3 or by 1.732. I tend to apply the KISS principle, and I find it far easier, bear this in mind, that if I work with line values to calculate power, I've always consistently am working with the root of 3 or 1.732. It's not to say that you can't use phase values, but you have to remember that when you're using phase values of voltage and current, you must multiply it by 3. I try and avoid confusion. So I work with line values, and my work is a little bit more accurate because I'm making less mistakes. Now, enough said. We'll take the value of line current. In this case, it was 601 volts. We're going to multiply it by the 26.69 amps. And we're going to multiply that by, you guessed it, 1.732. Now, inputting this into a calculator, which I've already done, got my cheat sheet, your value for volt, amps, reactive, capacitive is going to be 27,782.48, and again, rounded to 2 decimal places. So we basically have filled in all of the missing values for the capacitive load bank. Now we're going to input this, and we're going to start moving down through the circuit, and I'm going to start working on the inductive load bank next.
So we've already got our value of reactive power for the capacitive load bank. This branch has now been completely filled in. We're going to jump onto our inductive branch just because of the fact it is Y connected. So there's an awful lot of similarity, and I'd like to kind of continue in that vein or in that direction. So when we're looking at it, the same thing is going to apply. I've got a value of inductive reactance as well as the value of phase voltage. It's just a matter of applying Ohm's law, and we're going to calculate the current draw for each of the inductors in this Y-connected inductive load bank. So let's proceed to doing that calculation.
So we've started our preliminary work of finding the current draw of each of the inductors in a Y-connected inductive load bank. We're going to be using the following formula, where I phase is equal to the E phase. Now we've calculated that previously, and we're also going to divide that by the value of inductive reactance, or X sub L. We're going to take the 347 volts, and we're going to divide it by the 18.7 ohms. That is going to give us 18.56 amperes. Now, bear in mind that this is a Y-connected load, and that I phase is equal to I line. That means then that this 18.56 amps can actually be carried over from the phase value, and also we are going to use it as a line value, because that's one of the characteristics of a Y connection. It acts an awful lot like a series circuit. So we're going to input that, and we're going to be right back, because we're going to calculate the reactive power next.
Now, the only thing that remains is we're going to calculate the value of reactive power that the inductors must absorb in order to function. So we're going to use Ohm's law again. We're going to take line values, in this case, the 601 multiplied by the current, which is 18.56, multiplied by the square root of 3, which happens to be 1.732. So we're going to go down there and get that done, and we'll be right back.
So we're on to step 6, which is establishing the amount of reactive power that is going to be absorbed by our inductive load bank. Now, it seems very repetitive. The only thing that is different in this formula is that the notation, we're looking at volt amps reactive inductive, but everything else remains the same. We're going to be using line voltage multiplied by line current multiplied by the root of 3, 1.732. So let's get to it. So our 601 volts multiplied by the 18.56 amperes multiplied by 1.732. We input this into a calculator, being mindful to be accurate, and you should get it 19,319.7. Now this was rounded to 2 decimal places, and we're going to input that into the chart. And we have just finished calculating for all of the missing values for the inductive load bank. Now,
so we've got the inductive load bank completed. Now what it remains is start to do our work on filling in for the missing values for our resistive load bank, which happens to be delta connected. Again, this may seem very repetitive, but what we're going to do is use phase values for the voltage. We're going to use the resistive value, and we're going to calculate the current draw for each of these resistors. So we're going to move down and continue on this process.
Step 7, we're going to calculate the amount of current each of the resistors is drawing from that resistive load bank, being mindful of the fact that that resistive load bank is a delta connection. Now, it doesn't change the process because we're still going to use the phase value of voltage, and we're going to divide it by the resistance. In this case, because it was delta, it is 601 volts divided by 29 ohms. And that's going to give me, as a result, 20.72 amperes. I'm going to go ahead and input that in the chart, and then we're going to jump to step 8. Now, because of the fact that we have a delta connection, this value of current is actually going to have to be calculated for the line value. But let's not get ahead of ourselves just yet.
Now that I've calculated the current value across the phase, I need to calculate for the current on the line. This being a delta connection, I'm going to have to take the phase value and I'm going to have to multiply it by the 1.732. So that's what we're going to do next.
Our next step, we're going to calculate the line current. We're basically going to use the following formula, which is I line is going to be equal to I phase multiplied by 1.732. In our case, we're going to take 20.72 amps, which is what we calculated previously, and we're going to multiply it 0.732, and as a result, I'm going to have 35.89 amperes. We're going to go ahead, put that into the chart, and then we're going to come back and we're going to start calculating the value of power for the resistive bank.
Now that we have the value of line current, we're going to be using that information in order to calculate for the value of power consumed by my resistive load bank.
We're at that point where we're almost finished completing the values for the resistive bank. Number 9, we're going to compute the true power of the resistor bank. Now you'll notice I never put down a note whether it was delta or it was Y because it's irrelevant. When we're calculating values of power, we're just going to start using line values. So P is going to be equal to the value of line voltage multiplied by the value of line current, and again by the root of 3 or 1.732. Now, what was the line voltage? Oh, that's right, 601. So 601 volts. We're going to multiply that by what we had calculated, the line voltage, 35.89 multiplied by 1.732. Now, can't forget the equal sign. Power is equal to, drum roll please, 37,363.43. So this basically finishes off all the values that we had for our resistive load bank. Now, once I put this into the chart, we're on to calculating the remaining values that need to be supplied to us from the secondary of that transformer. So I'm going to move down there and start adding these values, and we're going to move on to step 10.
Now that we've established values for the entire circuit for power, reactive power, inductive, reactive power, capacitive, it's just a matter of using trigonometry now to calculate the overall apparent power for the entire circuit that's going to be drawn from the secondary of my transformer. So we're going to move down and we'll do this calculation, And once we have that calculation, that's going to unlock the value of line current as well as impedance and phase current. So
now we're starting to move on to the actual secondary of the transformer. Now when I was writing this, it occurred to me that I should really clarify. When we say we need to calculate the apparent power that the transformer secondary is going to provide the circuit, it kind of puts it out there that a transformer supplies power, but in reality it doesn't supply power, it merely transforms it. Power is actually going through the transformer, and I wanted to be very clear that when we have a transformer, power in is equal to power out. And so I just want to make sure that I am not leading people off or astray by this sentence. The secondary is going to provide all of the reactive power and the true power, and is basically going to be drawn from the primary, and the primary gets that from the power supply. So I just want to be crystal clear on that point. So I'm going to erase this, and we're going to proceed to looking at the formula, which is a trig formula where we're looking at the apparent power of the circuit is the result of the amount of true power squared plus, we'll open up the brackets, we take the reactive power of the inductors and we subtract the reactive power generated by the capacitors, close the brackets, squared, and square root. Now, I'm going to have to grab my cheat sheet here because I can't remember, they were very large numbers. But if we input that, so we had 37,363.43, that was watts, squared, plus, we're going to open the brackets. For the inductors, it was 19,319.7. We're going to subtract from the capacitors 27,782.48, close the brackets, square, and that's a long line, and so we're going to input this into the calculator, being very mindful that we don't make a mistake inputting the numbers. And you should be getting for an answer 38,309.85 volt amps. So we're going to go and put that into the chart, and we're going to discuss where do we go from there. Now that I have the value for apparent power, I can either start working to get the missing values here, or I can work on solving for power factor. I think I'm going to start working at filling in these values first, then I'll come back to do power factor and eventually angle theta. So the first thing we're going to do is figure out the value of line current. Now I drew out one of the original formulas because I wanted to show people how this formula gets manipulated in order to isolate for the value of current. We're simply going to manipulate it to isolate for the value of current. So I line is going to be equal, put that down here. So if I subtract this, E line, the voltage, multiplied by the 1.732, these basically have to be taken and brought down here on this side. So we're going to use the value of apparent power, and we're going to divide it, but we're going to have to remember we have PEDMAS rules to remember. So a set of brackets, we're going to take the line voltage multiplied by the 1.732. An awful lot of people will look at it and they say it just seems counterintuitive, but the formula is accurate. So I'm going to input my values just down here. So the value of line current will equal to the VA, which was, in our case, 38,309.85 VA, head mass rules, and we had 601 volts multiplied by that 1.732. And that's going to give us, for a value of current of 36.8 amperes. Now, we have this. We could go ahead and start calculating the value of phase current, but this is a Y-connected secondary, right? So this is Y. And one of the characteristics of the Y connection is that I line is equal to I phase. So this 36.8 can just as easily be put down as a line value, and it doubles as a phase value because it is Y connected. So we're going to go and put that in, and then the next calculation will be to calculate for the value of impedance, 36.8 amperes. Now, it's just a matter of using the phase values to calculate for the impedance of each of these coils that make up the secondary of my transformer. So that's what we're going to do next. I want to be clear on this one point. Step 12 involves finding the impedance of the circuit, or Z, not to be confused with the internal impedance of the transformer. Those are two separate things. What we're talking about here is I want to find the overall impedance of the circuit, and so we have to use phase values in order to be accurate with this. And it is an Ohm's law formula where Z will be equal to the value of phase voltage divided by phase current. Now, we just take our 347 volts and divide it by that value of current, which was calculated at 36.8 amperes. The result of this should be 9.43 ohms of impedance. It's now time to start shifting our focus into finding the values of power factor and eventually angle theta. Now, it bears mentioning that the VA that we've calculated here for the secondary is going to be the exact same value as that we are going to list on the primary. One fundamental thing that we always have to remember is that when we're dealing with transformers, power in is always going to be equal to power out. Transformers only change the ratio of voltage and current. In this case, we have a step-down transformer, so I've got a higher value of voltage, in this case 4160, and I'm going to step it down to a lower, more manageable value of 347 volts. But then again, I'm going to have a drastic increase in the value of current across the phases. And that's what the transformer is going to do. We're going to change values of voltage and current. It can't change frequency, and it doesn't affect power. So let's go ahead and put in that value of VA, or apparent power. Now, for those of you that may not remember, power factor is simply a ratio based off of true power and apparent power. We're going to take the value of P and we're going to divide it by the value of VA. Now, because this is trig, we don't have to do anything in terms of multiplying it or subtracting it by the root of 3. That's already been done. So this is a very straightforward calculation. And now we're going to calculate power factor. I've always maintained the easiest way to remember how to calculate power factor is remembering that it's based off of a ratio, and that ratio is the value of true power to apparent power. Regardless if it's the secondary of a transformer or if it's a three-phase circuit, makes no difference. It's still the same calculation and the procedure doesn't change. So let's put those values in there.
So we've got 37,363.43, and this is watts. And we're going to divide that by the power, the VA, the VA, which was 38,309.85, and again, that was VA. So our power factor would be equal to 0.9753. Now, this is normally expressed as a percentage. Now, you can either multiply it by 100 or take the decimal and move it 2 places to the right. So 1, 2, and you're going to end up with 97.53%. Now we're going to move on to finding angle theta.
Now, moving on, I have the power factor calculated at 97.53%. To find angle theta, the formula is the cosine of the power factor is equal to angle theta. If we manipulate this, because we have to isolate for the power factor, you're basically, oh, you know what? I made a mistake. It is the cosine of angle theta is equal to power factor. My apologies. But what you have to do is isolate it. So that means then that angle theta is going to be equal to the value of power factor, and then it'll be negative cosine. Now, this is a percentage. It has to be broken down back into a decimal. In this case, angle theta will be equal to 0.9753, and then chances are you may still have this value still in your calculator, and all you would have to do is hit negative cosine, and you're going to get your value of angle theta. Now, angle theta and power factor are kind of inversely proportional. So I've got a really high power factor, so the phase angle difference between the voltage and current is going to be very minimal. And true to form, the value I got when I did the calculation was 12.76 degrees. So that's the amount of phase angle difference between the input voltage and the current coming from the secondary that is feeding the circuit. So now that that's done, what we're going to do is start calculating values of the primary. So I'm going to go and input this, and we're going to be right back figuring out what's left on that primary. Now that I've finished calculating the power factor, and while I was at it, it was a very simple procedure to calculate for angle theta. We know that the voltage and current are going to be out of phase by 12.76 degrees. Now obviously we would need an oscilloscope to either confirm that, but mathematically this is what it comes out to. Now I can either start calculating for these missing values, or I could just go ahead and use the values of voltage in order to calculate ratio. Now I could either use voltage, but I could also use current values for the phase. One or the other, it makes no difference. I think what I want to do is I'm going to calculate the value of line current and proceed from there, and then we'll start looking at our phase values for current. Oh, before I forget, remember our primary is delta connected, and as we saw over here, when you have the delta connection, the line value of the voltage is the same as the phase value of the voltage. So this 4160 value can actually be brought down and inputted here. Now that I have these two values, I have the apparent power as well as the line value, it's simply now a question of repeating the same step that we used over here to calculate the line current, but on the primary side this time. Well, it was pretty easy figuring out the VA for the primary side of the transformer. Power in is equal to power out. Now, what we're going to do is find the line current on the transformer's primary. We're going to be using the VA. So I line is going to be equal to the VA, and that is going to be divided by the value of line current multiplied by 1.732. Now this is the exact same formula that we used previously on the secondary side. Nothing changes. The only thing that really changes is the values. In our case, 38,309.85 VA, and that was the 4160, because this is a delta, and let's put that down. That we have a delta connected primary, so the 4160 volts multiplied by that 1.732. Again, following PEDMAS rules, it's really important we put these brackets in here, and as a result, your value of line current is going to be 5.32 amperes. So we're going to input this into our chart, and then we're going to come back because I need to find phase values. And so there you have it. We've calculated for the value of line current on the primary side of the transformer. Now, the only value that remains is the phase current. We're going to take the line value and we're going to divide it by 1.732, which is going to give us that phase value we're looking for. We're going to get I phase, or we're simply going to take the line value, so I line, and we're going to divide it by the value of the root of 3, or 1.732. So that 5.32 amperes gets divided by the 1.732. As a result, you should be getting 3.07 amps in the phase, which goes a long way of establishing that when the step-down transformer, I've got really high voltage with low current, and by the time we get onto the secondary, I've got low voltage, but now the ratio, I'm going to have high current. And this holds true right here. Now, the only thing that's left is we're going to calculate ratio, but not before I enter this. So there you have it. We've calculated for the current on the phase, which was 3.07 amps. And as I mentioned before, now the only value left to calculate would be the ratio. As I said earlier, I can either use phase values of voltage or current. It comes down, it's a ratio. In this final step of determining the turns ratio of the transformer, I do have some options. I can either elect to use the voltage values of the primary and the secondary phases, or I can use the current of the secondary and the primary. Again, they are phase values, and that's a really important note that we must be using phase values when determining either impedance or your turns ratio. Now, I elected to do it both ways, just to demonstrate that the numbers are going to come out the exact same. And in our case, what you're going to have is the phase voltage of the primary is 4,160 volts, divided by a phase voltage of 347 volts. That is going to give you 11.99. Now that's rounded to 2 decimal places. When I use the current values, you have secondary on the phase of 36.8 amperes divided by 3.07 amperes. Putting this into a calculator, you're going to get roughly the exact same number of 11.98, but when you round it to 2 decimal places, you end up with 11.99. So there you have it. What we did is we took essentially a very complex and intimidating circuit calculation, and what we did is we worked at it in stages, breaking it down step by step, device by device, working either by the secondary side, each load taken by its value, and we were able to accomplish something that could have been very, very intimidating, and we made it look easy. I hope. Well, thank you for tuning in to another episode of Tales of the Workshop. Hopefully you got something out of today's presentation. As you can see, it was a very in-depth circuit. It took a lot of time. It took a lot of patience and attention to detail. But as you can see, with a little bit of persistence, anything can be accomplished. So until next time, please stay safe. And if you're enjoying these videos, please hit like and subscribe.